Okay, why don't we go ahead and get started again. The second half, when we left our hero last time, she had analyzed all our anatomicals in FreeSurfer. She had unpacked each subject into the FSFAST directory structure. She had created a subject name file. She created a paradigm file that coded the stimulus schedules and copied it into the run folders. And she'd done preprocessing, which was the motion correction, slice timing correction, possibly B0 correction, registration to the anatomical, resampling into the common space, either the left hemisphere, right hemisphere, or subcortical, and done smoothing on it. So what's left after that is data that has been preprocessed, and so and on a given left hemisphere, you'd have a vertex, and that vertex is going to have a time series. And so now we're ready. The preprocessing does not reduce the dimension of the data. So if you start with 100 time points before preprocessing, you have 100 time points after preprocessing. So the various levels of analysis now are data reduction steps. So you're going to take those 100 time points or 400 time points or 1,000 time points and reduce them down to a few numbers and eventually down to one number per vertex, per subject. And then in the group analysis, you take that one number per subject over your 100 subjects and you reduce that down to one number across all of your subjects. And then the multiple comparisons takes all the numbers across the surface or the volume and reduces that down to one or two numbers, depending upon how many clusters you have. So the preprocessing is not a data reduction step. It is just a preprocessing step. So now we enter into the data reduction process by configuring the analysis. So the first level, general linear model, you're going to specify the model for your task. So that can be event related or blocked. We have something called AB blocked, which is periodic two condition retinotopy for those who are interested in visual processing. And you specify the task timing with a paradigm file and a hemodynamic response function, and then the contrast. And then you also specify noise models and nuisance variables. So these are like low frequency drifts, so you can see inside of the scanner. If you just put a pot roast into the scanner and scan it for 10 minutes, you'll see that you might have some slight drifts up or some slight drifts down. You might have places where the subject, has a head jerk or there's a spike in the scanner and you want to just remove a couple of time points. You might include motion correction parameters as regressors of no interest. And you might also have some kind of physiology if you're measuring heart rate or respiration or entitled CO2 or something like that. And then there's another aspect of the noise, which is temporal whitening. So just to refresh your memory here, so this is something that Jung Yu showed yesterday. So this is a flashing checkerboard on and off every 15 seconds. And then this is a raw time series. So this is coming out of a single preprocessed voxel or vertex. And so, basically the fMRI analysis at this stage is a correlation between the known stimulus timing and the raw data. And then that correlation gives you one number, which is the data reduction step. So what we really do is to say that this time series, this raw time series, is equal to a weighted sum of factors. And those factors are your regression coefficients, and they're created based upon your stimulus paradigm. So in this case, this is the odd block here in red. So it's the odd blocks have this very sharp boxcar looking kind of shape to it, and then you convolve it with the hemodynamic response and you get your regressor out. And so eventually what you have to do is to be able to specify all of this information in one place. So in FSFAST, as I said before, I'm a little bit obsessed with automation. I'm also obsessed with reproducibility, and so I've made the streams such that you always have to analyze your data. All your different subjects have to be analyzed in exactly the same way, and if not, then something will break. And so the way that I enforce that is that I have the user create this, configure this analysis, which is just the collection of parameters of how you want to analyze the data. And that's done with this mkAnalysis-sesh command. And then you also create contrast with this mkContrast command. And so this is something that you do once, regardless of how many subjects or sessions that you have. And you can actually do this before you even have collected the first voxel of data. And then for each session, then you run this analysis with selexaf3-sesh. So this mkAnalysis command, it's a little bit intense, and I know you look at these things and you go, oh my God, is he going to really go through all of these command line parameters? And the answer is yes. And you know, it's not any more fun for me than for you, but it's something that you have to do, right? So you would cd into your project directory, and you'd have your sessions underneath there, and you would run a command that looks something like this. And so when you run this command, you give it a -analysis option, and you tell it the name of the analysis. And this name can be anything. You know, it can be, you know, Dorothy. It could be oddeven.sm5. It could be object.sm6. It can be anything that you want it to do. And when you run this command, it's going to create a folder in your project directory called analysis.info. And this analysis name is then going to be used for every time you want to access, you know, this particular analysis with these parameters. You then tell it the pre-processing options that you use. So for in this case, you would have FS average and then the left hemisphere, and you would smoothed it by 5 millimeters. And then it knows how to go down and get the pre-processed data. And if you had included slice timing correction or Bezier distortion correction, you would also include them as part of this command line. As I said before, like you have to do something for the left hemisphere, something for the right hemisphere, and something for subcortical. And so this mkAnalysis command has to be run for the left hemisphere, for the right hemisphere, and for the subcortical. And so this just shows the command line that you would use to run it for the subcortical analysis, assuming that you're going to use the linear registration to the MNI 305, which is what FS average is. And it's also possible to use CVS here, as I mentioned before. You specify what the paradigm file is, so it's pretty straightforward. In this case, I tell it that it's an event-related design. Mathematically, event-related and block designs are identical. There's no difference in the way that things are analyzed. So for this flashing checkerboard, even though it's a block design, I still just put event-related. SPM HRF 0. So as we mentioned before, when your paradigm file just says, you know, this stimulus came on here and turned off there, and this other stimulus came on here and turned off then. But we know that the hemodynamic response does not change in that Sharpe fashion. So when you have block design, the hemodynamic response isn't going to come up instantaneously and turn off instantaneously. It's going to have some kind of sluggish response because you're basically dealing with plumbing and not electricity. And so the way that we model that is to convolve it with a hemodynamic response. And so, you know, in my also obsession with flexibility, I've added a number of different hemodynamic responses that you can use. So there's an SPM canonical one, there's the one that's used in FSL, and then I have one that I used in FSFAST for a long time. But most of the time I just use the one from SPM, and that's designated by this -SPM HRF. And then 0 is the number of derivatives I'm not a big fan of adding derivatives into a design matrix, so I usually just use that as 0. So most of the time, it really doesn't make much of a difference. If you change these hemodynamic responses and you reanalyze all your data, you'll get very small changes in the output most of the time. So I usually don't sweat it very much and just use the SPM HRF. The reference event duration. This is something that's a little bit difficult to explain, but basically you just set this to the duration of your event. So if, like in my block design that I have here, it's 15-second blocks. So I just set it equal to 15. In general, this is like ends up being a type of scaling parameter. So it will have no effect on your p-value at all. So you can just set it to 1 if you want to. The one thing you shouldn't do is to set it to 0. So this has to do with if you're going to report, say, the amplitude of the hemodynamic response. So you did your analysis, you found a cluster where interesting things were happening, and you wanted to report the percent signal change. This is actually a surprisingly difficult thing to report, and I've had long discussions with Steve Smith, who wrote the FSL tools, about this very problem, and they don't have a great solution for it either. So without getting into the gory details of it that are very esoteric, you can just set it equal to your event in seconds, and then if you report percent signal change in your results section, then it's actually going to mean something. Polyfit2 says to use a second order polynomial. So this is to account for drift in the scanner. So as I said before, you could put a pot roast in the scanner and scan it, and you can see these things that are changing slightly up and down, or maybe quadratically. And so this is basically helping to remove this low frequency drift. So you can also use motion parameters as nuisance variables. So if you remember yesterday when we talked about measuring and removing motion from the fMRI scan, you put a subject in there, and they're in there for like a couple of hours or whatever, and over the course of your 5-minute or 10-minute fMRI run, they're going to get in there and they're going to start moving around, right? And there's actually 6 ways that you can move your head. So you can move it kind of like left and right, move it forward and back, move it up and down. You can nod your head yes. You can shake your head no. And you can do that, which I guess is maybe. So those are the 6 ways that you can move your head. And so at every time point, the motion correction algorithm is going to measure those 6 dimensions. And so you have a list of number of time points by 6. And so a lot of times people like to take those and throw them into the design matrix, because as you start moving around, it's going to affect the signal. I'm not a big fan of this, and if somebody's interested, I can go on at length as to why. But a lot of people end up doing it, and so I add it as an option. It's probably more important for doing resting state than for task. And you can add arbitrary regressor files as well. So if you have physiology or something like that, or like the mean of white matter or the mean of CSF or some other kind of nuisance file, you can include them with this nuisance regressors. I tell it in skip 4 rather, and this just says to skip the first 4 time points, because sometimes the scanner hasn't reached full magnetic equilibrium until 2 or 3 or 4 acquisitions into the scan. This tells it that the TR is equal to 2 and that the number of conditions is equal to 2. So the number of conditions is the number of conditions you have in your paradigm file. So excluding fixation. So in this case, for my odd and even task, I just have task 1 and I have task 2. So I have 2 conditions in my file. And so I put 2 here. So that's how you configure the analysis. And when you're done with that, it's going to create this file that has a collection of all these parameters that fully specify how you're going to analyze the first level. But you haven't analyzed anything yet. All you've done, so this command, this MK analysis command, runs in seconds, because all it's doing is just collecting these parameters and putting them into one place. So now we can talk about creating the contrast. So if you remember back to this design matrix here, I have Y, which is the raw time series, or the preprocessed time series at a given voxel. And then I have my design matrix. I have my on blocks convolved with the hemodynamic response, the off blocks convolved with the hemodynamic response, and maybe some low frequency drift term here. And so because I have 3 regressors here, I'm going to have 3 regression coefficients. I'll have the beta odd, which is going to be the hemodynamic amplitude to the odd block, the beta even, which is going to be the hemodynamic response amplitude to the even block, and then a nuisance one. And so probably I'm going to be interested in looking at, say, the difference between these two. You know, this could be happy or sad or whatever. And so the idea being that there's some kind of, the neural response is proportional to whatever these beta coefficients are. And so I'm going to form a statistic by taking the difference between the odd and the even. And this is where I get my contrast matrix from. So this is kind of the general theory of what a contrast is and how you create a contrast matrix. And so in FSFAST, we do this in a particular way using this MK contrast command. So when I run it, I pass it the name of the analysis. So I'd already made this analysis called oddeven.sm5.lh, and that folder already exists, and that analysis.info already exists. And if you look inside of that, you'll just see all the parameters that you selected earlier before. So now I give it a contrast, and I give it a contrast name, say odd versus even. And this is just a name, a label that you can give it, and it's going to be used further down the road. And after you're done running this command, it's going to create this odd versus even.mat file. And then you start giving it the contrast or the conditions that you want to compare. So I have a -A flag and a -C flag. And a -A flag says that this is an active condition. And in the contrast matrix, that means it's going to get a +1. And then -C says this is a control condition. And that means that in the design matrix, it's going to get a -1. And in this case, I don't need to worry about my nuisance regressors. FSFAST knows what's nuisance and what's task, and so it's only going to be working with task regressors here. So in this case, I selected -A1. So if I go to my paradigm file for condition number 1, I see that's task odd. And I say -C2, and I go to my paradigm file, and I see that condition 2 is task even. So what this is going to do is it's going to compute the task odd minus the task even, because I gave it -A1 and -C2. If I was interested in just looking at something versus baseline, so oftentimes I like to do this when I analyze my data, even though it's not necessarily going to be a condition of interest. You know, if I'm looking at like emotional faces, and I have a happy face and a neutral face, I'm not so interested in what is the response of the brain to the happy face by itself, or what is the response of the brain to the neutral face by itself. I'm really interested in what the difference is, because that's going to tell me the vertices where the brain is processing emotional faces. But sometimes I like to look at something like happy versus fixation, because that allows me to make sure that everything is kind of working. So in that contrast, I expect to see a lot of, say, visual activation. And if I don't see visual activation there, then that might be an indication that there's something that's going wrong. So to do this in FSFAST, I would say -A1. So 1 again is the task odd. And I say -C0, and 0 is the fixation. So in this case, this is an implicit contrast versus fixation because fixation doesn't actually show up in my contrast matrix. So this is trying to set up contrast is probably one of the most difficult things in fMRI analysis, because everything else can pretty much be automated. But setting up contrast and maybe setting up the paradigm files are the two things that the user has to do. And it's not something that I can necessarily help you with, because I don't know what your design is and I don't know what your hypothesis is. So the contrast ends up being an embodiment of the hypothesis that you want to test. So, oftentimes, the people who are running these things that don't necessarily have a lot of mathematical sophistication or statistical sophistication. That's why you rely on us, the tool developers. But this is the place where, these two things meet. And so you're the only one who knows what your hypothesis is and what you're trying to test. So you're the one who has to be able to convert your hypothesis into contrast. And so it's not necessarily an easy thing to do, but it's not terribly hard, I think. It's just a little bit confusing sometimes. So I created this example to help explain how we do this in FSFAST. So let's say that I had a design where I was looking at happy faces, sad faces, and mad faces. So an emotional faces task, pretty common. So one hypothesis would be that the response to happy is different than that to mad. So I would have MK contrast. I would say, okay, I already have an analysis set up, and I'm going to call this contrast happy versus mad. I'm going to say -A1 and -C3. So -A1 says to use the happy face as the positive contrast, and -C3 says to use the mad face as the negative. So what this is going to do is it's going to take happy and subtract mad from it. So note that I'm not saying anything. My hypothesis doesn't say anything about sad, and sad is not represented here because I don't have a -A2 or a -C2 there. So sad is not represented. Maybe it's something that I just needed as kind of to engage the subject in this particular task, but I don't have a hypothesis about it, or maybe I have multiple hypotheses. And in this particular hypothesis, sad isn't represented. So in this case, I would just give it a -A1 and a -C3, and that's going to compute happy versus mad. So alternatively, I could say that my hypothesis is that the response to happy is different than the average of the response to sad and mad. So this would be looking for, say, kind of like a positive valence versus a negative valence. So in this case, I am engaging all three of the stimuli that I've presented to the subject. So I run MK contrast, I give it the analysis that I created before, and in this particular contrast, I'm going to call it happy versus sad mad. So I'm looking at happy versus sad and mad, so I'm going to say -A1 to make happy the positive contrast, and then I say -C2 and -C3, and what that does is it says that sad and mad are the negative contrast. And so what FSFAST is going to do is that it's going to take the hemodynamic response to happy and compare it against the average of the hemodynamic responses to sad and mad. And that's shown in this contrast matrix as the 1 as the first element, and then -0.5 and -0.5, because that's the 0.5s are going to compute the average of the happy or the sad and mad, and then the minuses are going to say, take it as a negative contrast there. So you, in the tutorial, you'll have a situation where you have 5 or 6 different conditions. And so you'll be able to create all kinds of different contrasts. And you can see that, if we're you could imagine making like 3 or 4 more different contrasts just from this simple design. So, if you have a fairly complicated design with 4 or 5 or 6 contrasts, you can start, there's a combinatorial explosion for the number of contrasts that you can make. So to summarize the configuration, so you CD'd into your project directory and you ran MK Analysis and MK Contrast. It created a folder for the analysis, and it created this analysis.info file with information about how you're going to analyze the data, and then it creates a .mat file here for each contrast that you had. So you'll have to do this for the left hemisphere, the right hemisphere, and the MNI 305. And then and you specify the preprocessing you want, the task, the nuisance variables, the noise, and the contrast. And it does not analyze the data. It just creates these configurations. So you should be able to create these things in a matter of minutes. And you can do it before you've ever collected the first voxel of data. And you do this once for each one of the spaces that you're interested in. You do it once regardless of the number of sessions that you have, and should only take a few minutes to run. So now you're actually ready to analyze data, and that's done with this cellxf3-sesh command. So you run it something like this, where you give it cellxf3-sesh, you give it all the sessions that you want, and you give it the name of the analysis. So cellxf3, this has a long history. So when I first arrived at MGH now like 20 years ago, and I was working with Anders Dale, he had a program called CellAvg, standing for selective averaging. And so when I started working for him, I enhanced his program to use matrices rather than selective averaging. So I stuck an X in there, and so the program was called CellXav. Because X is kind of like a matrix, and it's also kind of cool to have X in your command names. And then I improved it, and I called that one cellxav2. And then I improved it again, and now this is called cellxav3. So it's like selective averaging with matrices is what it's supposed to mean. So sometimes it's interesting to know, like when you see something really obscure like cellxav3, like where did that come from? So what this does is it goes through every session in your session ID file, and it finds the raw, or in this case the preprocessed data. It knows what the paradigm file is, and it finds that, and it finds all the external regressors. It constructs the design and the contrast matrices. It combines the runs together using smart concatenation. So first and second level analysis, and then it fits the design matrix to the time course at every voxel separately, and then it tests the contrasts at each voxel separately, and it does that for all of the sessions. And again, this may take a few hours depending upon how many sessions you have, and it does not rerun it if the data is up to date. So again, this is a nice feature of FSFAST. Regardless of how many sessions you have, you can just run this thing and it'll figure out what has been updated and what needs to be updated. So if at some point you say like want to go and add a contrast, say to your analysis, even though you've already analyzed some of your data, you would just run MK Analysis-sesh and it would create a new contrast file. And then you just run cellxf3, and it goes off and it generates all the new contrasts for you. And so if you run this a second time immediately afterwards, then it should return in a few minutes, because it can say, nothing needs to be done. So the question is, when you run cellxf3 and you do the GLM fit, does it fit it all for one session? or does it somehow combine sessions? Or
Yeah, so are the runs being combined?
so the runs are being combined using something I call smart concatenation. So basically, it uses a single regressor for all your tasks, but a different regressor for all your nuisance variables. So, but it concatenates all the runs together, but then it's careful to make sure that the nuisance variables are fit independently for each run, but the tasks are fit the same for each run. And this SelectF3 requires MATLAB. It will require MATLAB in order to run, whereas the preprocessing doesn't require MATLAB. Yep. Oh, sorry.
So this command should be run 3 times for left hemisphere, right hemisphere.
Right. This command should be run 3 times: left hemisphere, right hemisphere, and subcortical. Okay. So when you're done, the directory structure looks like this. You have your project, you have your session, you have your functional subdirectory. You now have an analysis under the functional subdirectory, and under that you have contrast. And inside of that, you have a whole bunch of files, but the most important ones are this CES, which stands for contrast effect size, and this is similar to like a COPE in FSL or CON in SPM. And then you have a CES var file, which is contrast variance, which is like a var COPE in FSL. And then you have a SIG, which is the significance, it's minus log P of the contrast. This is basically all of the output from running SelectSAV3. And then if you want to, you can visualize the individual subjects using this tk-surfer or tk-medit -sesh commands. All of these are going to run free view. So we used to have the tools called tk-medit and tk-surfer, and those were the default visualization tools in FreeSurfer. Those still exist, but they're obsolete now. FreeView is much better, but that's where these names come from. tk-surfer was the surface viewer, and tk-medit was the volume viewer. So you run it, similar to this. You give the session that you want, the analysis, and then the contrast. And you can also specify multiple contrasts. And what it looks like is something like this. So you can see the left hemisphere, you can see the right hemisphere, and then you can see the subcortical analysis. This is all on FS average. So after the first level analysis, as I mentioned before, your data structure looks something like this with the project, session, functional subdirectory, your analysis, your contrast, and then you have these 2 files, CES and CES var, and those are the ones that can be used in the higher level analysis. So at this point, it's a little bit similar to after you've run recon all, and you have like a thickness file. So that thickness file is 1 number per subject per vertex, and so you take that one number and you map it into the FS average space, and you stack all of your subjects together, and then you go off and do a general linear model. So it's basically the same thing here. So again, if we come back to this diagram, left hemisphere, right hemisphere, subcortical, we've just finished the first level general linear model where we've taken the entire time course and reduced it down to 1 number, which is this contrast effect size. And then I combine all of those numbers together across subject, and I have my FSGD file that creates a design matrix for the group analysis, and I have a contrast for the group analysis, and I apply that to that data, and that reduces it again down to 1 number, which is the p-value at every vertex, and then I do the correction for multiple comparisons. So these 2 steps are done with 2 programs called ISX concat -sesh and then MRI GLM fit, which you may remember from Tuesday morning. So ISX concat -sesh, so the name here, concat means to concatenate, and IS means intersubject, and X is just because X is cool to put into your name. So ISX concat -sesh, and you give the name of the analysis, you give it the name of the contrast that you want, and then you give it the sesh ID, and then you give it an output folder. So this is like running MRIS preproc in the anatomical stream. And so what this program does is it goes through and it finds the analysis for each session, finds a contrast, and extracts out this contrast effect size and concatenates them together into a stack, which it puts under this group folder, this analysis, and this contrast. So this is like the output of after you've run preproc-sesh, the CES file. This is just one number per subject per vertex. And then at this point, it's mostly the same as the group analysis that you learned with a couple of small twists to it. So again, you're going to run MRI GLM fit. You're going to say, the surface is for the FS average, left hemisphere. I should have pointed out here that for ISX concat -sesh, you would run it 3 times, one for the left hemisphere, one for the right hemisphere, and one for the subcortical. So for the left hemisphere, you'd specify FS average and GLM fit. You'd specify the input, which is this stack that you just created of contrasts. In a thickness study, this would be just the stack of your thicknesses. This is the FSGD file. So the important thing here is that when you run ISX concat -sesh and you specify a group sesh ID file, that the order that this of the sessions here is the same as your subjects in this FSGD file. You specify your contrasts the same way that you did before. These are higher level contrasts, so normal versus schizophrenic. So the one wrinkle here is if you're interested in, say, in interaction. Let's say that you have happy faces and neutral faces, and you have healthy controls and schizophrenics. And your final hypothesis is that you want to look for an interaction between the face valence and the diagnosis. So normally what you would do would be to get the response to happy for healthy controls, get the response to neutral for healthy controls, get the response to happy for schizophrenics, get the response to neutral for schizophrenics, and you would take those 4 things and you put them into a repeated measures ANOVA, for example. Here, we just break that up into 2 parts. So the first thing that we do is to compute a difference between happy and neutral for all subjects. And we take that difference, and then we take a difference between schizophrenics and normals. And that final number will end up being an interaction between diagnosis and face valence. So you just have to think about these things as you start with your highest level hypothesis and work back down to be able to create the pieces and parts that make that possible. The GLM group, it just says that you're going to have a folder. So this is the output of GLM fit, which is going to have a contrast, it's going to have a sig. And then finally, you have to give it an ERES save flag to save the residuals, which are needed for permutation. Finally, the final step is to correct for multiple comparisons. And this is going to be fairly similar to what we showed you on Tuesday afternoon. So you run this MRI GLM fit-sim command. You give it the output from the previous stage, which is the output of GLM fit. You say that you want to do permutation using 1,000 iterations with a contrast, a cluster forming threshold of 2, and say a positive group contrast. You could use negative, you can use absolute. You could say that you want to filter out clusters that are less significant than 0.05. And here we say that it's 3 spaces. So if you remember from a thickness analysis, we only use 2 spaces because you had left hemisphere and right hemisphere. In this case, you have left hemisphere, right hemisphere, subcortical. So we do Bonferroni correction over 3 spaces. And then that creates all the same output that you saw before, the most important of which is this summary file that will tell you where the significant clusters are. And so this is going to be what you would put into your results section along with the summary file for the right hemisphere and for the subcortical. For the subcortical analysis, assuming you're using the MNI 305 and not the CVS, you use the same exact ISX concat file. You just tell it a different analysis, and you can then give it the same output. So after you've run all 3 of them, you have an analysis for the left hemisphere, an analysis for the right, and an analysis for the subcortical. And then below, everything looks the same. So the GLM fit command ends up being very similar to what you had before. So it's basically exactly the same command line. The only difference is that you don't have a dash surf LH or RH in there. And then the simulation command is still exactly the same, and you still put in 3 spaces. So I think this is all basically just saying the same thing. And when you're done, you get a summary file for the MNI 305. So when you're done, you'll have 3 summary files, and then properly, each one of them properly corrected for multiple comparisons, and then that's what you would stick into your results section. Okay, so this is what it all looks like in the grand scheme of things. You have your project folder. Underneath that, you have your sessions. You have your subject name that allows you to link your fMRI data to your FreeSurfer analysis. You have a functional subdirectory. You have run data. You have the raw data underneath there, along with your paradigm file that encodes a stimulus schedule. You have an analysis and a contrast, and then the CES file is the contrast, which is the single number that you've reduced the entire time series down to. You would run ISX concat for the left hemisphere, right hemisphere, and MNI 305, and it would create these CES files at the group level, and you would apply your group analysis, your group design matrix through the FSGD file and your group contrast to create a left hemisphere, right hemisphere, and subcortical analysis. And if you wanted to, you could merge them all together into one volume for visualization purposes. So, sorry.
So if I want to compare between groups, I would have multiple groups.
Sorry?
If I want to compare between groups, so more than one group, I would have other subdirectory like group 2, group 3.
So if you wanted to compare across multiple groups, say you had schizophrenics and normals, you would do that all inside of one group folder. So the group is a collection of subjects in this case, and I didn't necessarily mean it to be something specific like a group of normals or a group of schizophrenics. Usually you would include all the subjects in your study inside of this particular group folder. So you've analyzed your data in FreeSurfer, you've unpacked each one of them with DCM unpack, you've created your subject name file, you copied your paradigm files in there, you've configured your analysis and your contrast, you've run your pre-processing, you've done your first level analysis, so that's a time series analysis that computes the betas and the contrasts. You run your higher level analysis using ISX concat and GLM fit, and then correction for multiple comparisons using MRI GLM fit-sim. And then I wrote this really nice program called publish-sesh that all you do, it writes your paper for you and submits it to the journal. It's really, really handy. It's been one of the more popular programs that I've written. Okay, now we're ready to start the tutorial. So I just want to tell you something about the task you're going to be working with the tutorial. So this was a task that we developed as part of the functional burn, which is a biomedical research network that I was involved in maybe, I don't know, 10 years ago or so. And this was a working memory task where subjects were, during an encode period, subjects were shown stick figures that look something like this. So you have a bed and a bell. And then there's a distractor period for 16 seconds where subjects are shown either emotional distractors like a car wreck or something like that. These are the IOPS pictures that can be very disturbing. Or it was 16 seconds of simply neutral, like, picture of a chair, picture of a tree, or something like that. And then after that, 16 seconds distractors, they were looking at, they had probes, which were stick figures. So it's a pair of stick figures where they either had to say the left figure was in the original list or the right figure was. So it's a forced choice task. So in this case, they would press the right button because the bell was in there. And then in this case, they would also press the right button because the bed was in there. So this gives us a possibility of 5 different conditions. So we have the encode condition. We have the distractor, which could either be emotional or neutral. And then we have the probe, and that probe could either follow the emotional distractors or it could follow the neutral distractors. And the basic idea here was they wanted to look at whether the distractor was going to be interfering with the memory recalled during the probe. So looking at the 4 versus 5 was their main contrast of interest. And they're also looking at schizophrenics versus normal. So this is one of those situations where they have to do this multi-level analysis, look at emotional versus neutral at the first level, and then do the contrast schizophrenic versus normal at the higher level. So in the tutorial data, you have actually 18 subjects that are there, and none of them are schizophrenics. These were pilot subjects that we ended up using. And so what you'll do is to go and start making analyses and start making contrasts, and you can run them and look at the results on the individual and maybe even on the group. Okay, are there any questions?